Does time exist? If we set aside complaints about never having enough time for anything, at first glance the question may seem absurd.
Of course it exists, but if you think about it for a moment, it becomes not so obvious.
Some even doubt not only the existence of time, but of just everything. The idea that our world is not real and that we live in a simulation is quite popular today. However, it is generally not embraced by scientists.
At the same time, there are things that we take for granted, but even they are not entirely straightforward. The first thing that comes to mind as an example is colors. Surely many of you have heard the statement, colors don't exist.
We seem to perceive colors as fundamental properties of various objects. Leaves are green, bananas are yellow, blue screen of death is, well, blue. But the thing is that what we see is just how our brain interprets light of different wavelengths. We can objectively say that green is radiation with wavelengths roughly between 520 and 570 nanometers. But we can't be sure that we all see the same green, and most likely we don't.
And most importantly, we cannot enter each other's minds to find out if my green is the same as yours. Vsauce had an entire video about that a long time ago.
It seems that color is an illusion. What if, in a similar way, time is also an illusion? And this isn't just some wild idea that pops into your head at 3 a.m. when you can't sleep. Scientists and philosophers have been debating this for a long time. Moreover, depending on the perspective and the definition of time, there is no universally accepted opinion on what it actually is. And in different interpretations of time, the view of the entire universe can change. For example, it might turn out that the future is predetermined and we can't actually influence anything.
Indeed, time is a strange thing, and let's delve deeper into it today. My name is Andrei, and this is Cosmos Elementary. Time. We sure do think and talk a lot about it. In the English language, time is often cited as the most frequently used noun. But to discuss whether time is real, first we need to understand what we mean by the words time and real.
In the dictionary, the word time has quite a few definitions.
If we take everyday definition, then of course time exists. There are many other immaterial things whose existence we don't doubt, and the concept of time we use every day. But whether something is real from the perspective of physics.
Astrophysicist Ethan Siegel, in his Popular Science article about the reality of time, presents several criteria that we need to consider if we want to understand whether something is real.
Can we measure it? Can we determine the quantity of it? Can we logically describe it mathematically? Is it an observed quantity intimately connected with other observed quantities?
While some might argue, and it's not that straightforward in every case, we can mostly answer yes to all of those questions, and in certain contexts it seems almost foolish to argue that time as a concept and a tool we use to describe the world exists. Of course it does. But when people talk about the illusion of time, they often mean something slightly different. Is time a fundamental property of our universe, or is it an emergent phenomenon?
Here's a frequent analogy. In the theories of physics, you won't find concepts like a dog, or a brick, or a table. But we don't doubt that those things exist.
Physics tends to operate with more fundamental concepts, such as particles, fields, and interactions, from which tables and dogs are essentially made of. In other words, tables emerge from more fundamental physics of particles.
And now, is time a fundamental concept, or it emerges from other fundamental components? And if so, what are they? Here, it's not very clear.
Well, perhaps time is something that our brain simply creates, similar to the case of colors. And, of course, this discussion is not without blatant misconceptions and incorrect interpretations.
There's a really popular book, The Secret by Rhonda Byrne. It's positioned as a self-help book, and let me quote a small excerpt from it.
Time is just an illusion. Einstein told us that.
Well, let me stop myself right there. Did he really? So even 100 years later, we cannot definitively say that. Okay, let's keep going.
Time is just an illusion, Einstein told us that. If this is the first time you have heard it, you may find it a hard concept to get your head around, because you see everything happening one thing after the other. What quantum physicists and Einstein tell us is that everything is happening simultaneously. If you can understand that there is no time and accept that concept, then you will see that whatever you want in the future already exists. If everything is happening at one time, then the parallel version of you with what you want already exists.
Whew. And what conclusion can be drawn from this? Well, here it is.
It takes no time for the universe to manifest what you want. Any time delay you experience is due to your delay in getting to the place of believing, knowing and feeling that you already have it. It is you getting yourself on the frequency of what you want. When you are on that frequency, then what you want will appear.
So typical pseudoscientific nonsense. And as they often do, they take something that really exists in science and flip it upside down to confirm their claims.
Another example of that would be, quote, "The universe looks like neurons," unquote. So if you think about something, it will happen just like that.
Where do all these ideas about time being an illusion or non-fundamental come from? Well, it all depends on the theory through which we view the world.
Hearing the mention of Einstein, one might immediately think of his theories of relativity and how they treat time. Also, those theories and quantum mechanics view time differently. Finally, in loop quantum gravity, it seems that you might get rid of time altogether. Many articles with headlines like "Scientists claim that time doesn't exist" often discuss research related to loop quantum gravity.
But let's go through everything step by step. I've just mentioned loop quantum gravity. One of the main problems in modern physics is that we have two very successful theories.
The general theory of relativity, a modern theory of gravity that describes how everything works on large scales, and quantum mechanics, which describes the physics of what happens on the smallest microscopic scales.
As many of you probably know, both theories work well separately and independently. They are confirmed in experiments and make very successful predictions. But these are very different theories, and they don't quite get along with each other, and scientists have been struggling for decades to unify them and construct the so-called theory of everything.
One of the well-known attempts to do this is the famous string theory. And another approach is quantum gravity. And one of its versions is loop quantum gravity. One of its founders, the Italian-American theoretical physicist Carlo Rovelli. He writes articles and gives lectures on the nature of time, and he wrote a whole book, The Order of Time. In his article Space and Time in Loop Quantum Gravity, Rovelli discusses several approaches to describing time.
Firstly, there is relative time. And let's not get confused by the name. Here we're not talking about Einstein's theory of relativity. Here, time is the relation between two events that we use to determine when they occurred. Here's an analogy with location in space.
If we have one planet in infinite empty space, how do we describe where it is? But when at least one more planet appears, we can already talk about where the first planet is relative to the second one. And with time, it is something similar, but not with objects, but rather with events. In a sense, you could say that there is no time if there are no events. But since there are plenty of events in our universe, time in this sense certainly does exist. Even Aristotle spoke about time in this manner.
The next option is Newtonian time. Newton actually had two concepts of time. The first is what I've just described, simply a way to determine how two events are located relative to each other.
But the second is the so-called absolute time, along with absolute space. In Newton's understanding, absolute space and time are separate entities that exist independently of objects and events. This is where objects exist and events take place. According to him, absolute time flows uniformly and consistently throughout the entire universe. Roughly speaking, there is some universal clock that shows true time, and ticks regardless of whether anything is happening in the universe or not. So once again, in the first time we had no time without events, but here it exists even without them.
Next, another person who changed our view of time was, of course, Albert Einstein, who developed special and general theories of relativity. And one of the consequences of both is slowing of time or time dilation. In the case of special theory of relativity, the flow of time depends on the speed at which an object is moving relative to another object.
You might recall that if we have two observers with identical clocks, one is at rest and the other is moving rapidly relative to the first one, the clocks of the one in motion will tick more slowly. And it's not just clocks, all processes work this way. But also the flow of time depends on gravity. That's general theory of relativity. The closer we get to the source of gravity, or the deeper in the gravitational well we are, the slower time flows. And again, it's not just theories. It has been experimentally confirmed multiple times. Without accounting for these effects, the GPS system wouldn't function correctly because the satellites in space are farther from the Earth and experience weaker gravity and are also moving quickly. On the one hand, Einstein showed that Newton was wrong with his absolute time. There is no universal true time, and time is relative. And of course, to top it off, that space-time is not static but dynamic. On the other hand, space and time can exist independently of matter and events.
And also, three spatial dimensions and one dimension of time in Einstein's theory are combined into a single entity, space-time. We can move not only in space and go right, forward or up, but also we're constantly moving in time. This, along with the fact that the speed of light has a finite value, is associated with the time dilation effect. As strange as it may sound, in the dimension of time we are moving at the speed of light.
And when we start moving in space, we slow down in time. And this is one of the ways to explain why we cannot reach the speed of light in the vacuum. Because otherwise, time would come to a stop.
Another important property of time is an apparent existence of a specific direction and its irreversibility. And that is connected to the concept of the arrow of time. When we move in space, there is no preferred direction. We can go backward, forward, right, left, and so on. But in the dimension of time, it seems that we have no choice and we can move only forward.
The arrow of time is essentially a concept that signifies the direction in which time flows. The question then arises, where does this direction come from?
It is interesting that most of the laws of physics are reversible in time, which means that if time were flowing in the opposite direction, they would still function the same way. Let's take gravity for instance. Here's a common example. Did I just play a normal video or was it in reverse?
The point here is that no matter in which direction I played, it will look realistic.
It's a different story when I release the ball and wait for it to stop. In the reversed playback, the difference will be noticeable, but here other processes come into play.
In short, despite the fact that most laws of physics are reversible in time, we still observe the arrow of time. One of the key ones is the thermodynamic arrow of time, the one about entropy.
In simplified terms, entropy is often referred to as measure of disorder. And in closed systems, entropy always increases, indicating that order is gradually moving towards disorder unless something is deliberately done to counteract it.
A plate can fall down and break. However, the shattered pieces of a broken plate will never spontaneously come back together to form a whole plate again. If we have two containers, one with cold gas and the other with hot gas, and we remove the barrier between them, gas will get mixed until the temperature is equalized. And it is considered that the entire universe behaves in a similar manner. Entropy in it constantly increases. And this shows us the direction of the flow of time towards greater disorder. The preferred direction is demonstrated by radioactive decay. We observe particle decaying into different isotopes, but not the other way around.
There's also a psychological arrow of time. We remember the past, but not the future. We cannot influence the past, but it seems that we can influence the future. We observe and measure all of this, and in this sense, it seems that time appears quite real.
But there is also the cosmological era of time and some others.
I mentioned earlier that quantum mechanics doesn't really go along with general relativity, and this extends to the concept of time in these theories as well.
As I mentioned before, according to Einstein, time is a full-fledged participant alongside space. Quantum mechanics, on the other hand, views time and space in a more classical sense, somewhat akin to Newton, as a backdrop against which everything unfolds. And also that at a quantum level, we no longer talk about exact states, but rather about probabilities, and time in quantum mechanics stands separately.
Loop quantum gravity attempts to reconcile those differences and make the fabric of space-time itself quantum.
According to Einstein, space-time is not something static, but rather something that can bend and warp under the influence of mass and energy. This concept is successfully confirmed by experiments and observations. The question is how nothing can bend. It's not matter, so what is space? Or more precisely, what is space-time?
And loop quantum gravity seeks to provide an answer to this question. And it is based on the idea that similar how to we and everything around us consists of small particles, the space-time itself is composed of the tiniest components.
In other words, if we take an absolutely empty region of space without any particles or fields, at the tiniest scale, there would be components from which space-time itself is made. These fragments are what are referred to as loops. They are the fundamental quantum components of space-time itself and are interconnected in a network. In this scenario, both space and time are no longer a continuum. That is, they are not a continuous medium. At a larger scale, space-time appears continuous to us, but at the smallest scale, it is not. Much like an image on a screen looks seamless until you zoom in enough to be able to see individual pixels. This applies to space and time. It may sound very strange.
We measure time in different intervals. An hour consists of minutes, minutes consist of seconds, and then seconds are further divided into smaller and smaller fractions. Loop quantum gravity suggests the existence of the smallest possible interval of time. This may sound confusing, but in this theory, the universe is ticking with the tiniest of ticks. Of course, I'm simplifying quite a bit. In reality, it is way more complex. In some non-academic articles, you may come across statements that loop quantum gravity completely eliminates time, which is not entirely accurate.
In the article I mentioned earlier by one of the founders of this theory, where he listed various approaches to time, Carlo Rovelli added notes to each point. He writes that time in general everyday sense is present in this theory. Indeed, in a certain sense, loop quantum gravity views time similarly to general relativity. However, this theory doesn't depict a continuous, familiar flow of time, but rather envisions time as being discrete.
Another perspective on the question of time lies at the intersection of physics and philosophy.
Certainly, many of you have probably tried to make sense of infinity. Despite the effort, there is still a desire to establish some barrier, but then what lies beyond that barrier?
And it seems to me that it is almost as difficult to truly feel and grasp what now is, trying to catch the moment. Is this now? Behind me, there is my constantly growing past, and I'm moving towards future. But where am I between these two times? Balancing on the edge of the knife, and what's the thickness of this blade? So there's a thing called Presentism. Presentism asserts that only what exists now is considered to exist. Conversely, nothing in time exists, except for abstract concepts, if it doesn't exist now.
If we compile an absolutely complete list of what exists now, the list might include, for instance, my phone, but would not include Aristotle from the past, or Martian colonies from the future, which makes sense. However, the contrast becomes clearer when we compare this approach with another, By the way, the question of what now is becomes further complicated by the relativity of time. For different observers located at a distance from each other or moving at different speeds, and so on, now can vary. Like the familiar example that in our now we can observe stars and galaxies that no longer exist. But we do see them.
In contrast to presentism, there is another approach, eternalism, or block universe. From this perspective, everything is real. Everything in the past, present, and future exists now. The universe is conceived as a four-dimensional block with 3 spatial dimensions and 1 dimension of time. What it would look like? Well, for the sake of simplicity, let's eliminate 1 spatial dimension.
Here we have 2 remaining spatial dimensions, and in this direction is the dimension of time. This is the block universe. Currently we exist on this thin slice of the present, which moves through the block. Naturally, in reality, it's not a cuboid and there should be an additional dimension, but this works well enough as a simple illustration. But unlike presentism, everything that happened in the past doesn't vanish from the existence. The entire block exists at all times, from our birth to our death, from the Big Bang to the end of the universe. We may not see that in our current now, but it's there. Similar to how we don't see objects that are far away in space, but they exist. And from this, several strange and even unsettling implications arise. Firstly, returning to the topic of the video, if everything exists simultaneously and equally, then the flow of time becomes an illusion. There is nothing inherently special about the present or now.
The word now can be compared with the word here. I'm now here, and my here is different from yours. In the block universe, the concept of now operates in the similar manner.
Furthermore, it turns out that time travel is possible here. Not only to the future, which is happening one way or another as we are moving into the future right now, but also to the past, perhaps using a wormhole or some other means.
As we well know, the problem of the concept of the time travel to the past is a bunch of paradoxes. And one of the most famous one is a grandfather paradox. We get back in time and eliminate our grandfather, but then how do we get born and go back in time to eliminate our grandfather? A paradox.
All those stories with the butterfly effect, altering events as in the Back to the Future, and so on, don't pose the problem in the block universe. The future cannot be changed because everything already exists. If we go back to the past, it means we must have gone back, or have already gone back. Neither the past nor the future can be altered.
And here's another unsettling conclusion. If everything already exists, does this mean that our future is predetermined and we have no free will? Doesn't sound very nice. But there's another approach, not as dramatic, and it is called growing block universe.
In this version, present and past are real, similar to eternalism, but the future can change. That is, the universe is continually growing in time because as time progresses, the past expands. Hence the name growing block universe. The present is like a barrier between the already existing past and as yet potential future. In this case, the future is not predetermined. Rather, possibilities are being actualized. Here we can go into all the multiverse shenanigans, the many worlds interpretation and other stuff, but now we're not going to talk about that. Time is a complex thing, and when we discuss whether it exists or not, it's important to specify the perspective from which we're looking at it. In any case, the answer usually leans towards yes. But what time is, how it flows, and whether it flows in the conventional sense, whether it is fundamental or emergent, we don't know definitively yet. There are no experimental confirmations of loop quantum gravity, and there is still no theory of everything. And yet, despite these uncertainties, we continue to measure and use time in our everyday lives. Surely in the future we will discover many more interesting aspects about it.
Thanks for watching. Links to all of the sources are as usual down below in the description. And you may have noticed that I don't get a lot of views, so if you really enjoyed the video, feel free to share it with your friends and maybe family. And of course, subscribe to get more videos in future. Bye!